Okay. Just on time. Well done. Okay. Second part of the lecture, sound perception and a little bit of physiological background. You don't get away from that because that's what I'm good at, that's what I do. I think it's interesting and it explains a number of things about perception of loudness and pitch. Talk about three kinds of perception today. The basis perception of sound, which is loudness, pitch and localization. You're probably, as musicians, most interested in pitch, I suppose, which I find most interesting as well by far, but they're all interesting in their own right. First of all, just 2 minutes about how we actually know about these things when we talk about physiology. Is we usually perform experiments by sticking electrodes into animals and playing sounds to them. The sounds that we play are short tone bursts, like something like that, 50 milliseconds sounds, and we stick an electrode, which is a glass pipette of about a few micrometers diameter, into the brain. This is a part of the brain called the cochlear nucleus, and usually it's a guinea pig, sometimes cats or other animals, and we can record individual neurons that are sitting in there. The recording, if you're successful in doing that, I've spent a few years of my time doing that exactly, is you're recording something like that over time. So the time scale here is about 50 milliseconds, and you measure voltage changes, and what you see here are action potentials of that nerve fiber. So auditory nerve fiber, usually we connect that to a loudspeaker and it sounds something like so you know you've hit a neuron if you hear that this neuron is responding. So it responds to sound, which means it's listening. And if that neuron is responding to sound, the brain is listening, because an action potential in an auditory nerve fiber that indicates yes, there is sound there. If it's the neuron happens to be in the visual system, it would mean you see something. If it's in the somatosensory system, it means you feel something. The brain doesn't differentiate. That's the language of the brain that it speaks, is these action potentials. Now, our job is to interpret how these action potentials code the message of sound. And one way of analyzing these is just to repeat, first of all, this simple experiment. So this red bar is the sound, 50 milliseconds sound. We do that 250 times, and every dot here is one spike, one action potential. You see that the neuron responds relatively always with the same way, namely it waits a little bit, then it responds a lot, it responds a little bit less, and then it doesn't respond anymore at all. To visualize that, we build a histogram of that. It's called a peristimulus time histogram, PSTH. We just count in every millisecond how many spikes there were on those 250 repeats. And I show you that because it shows a number of things about perception for this one single neuron. This is interesting. Namely, first of all, it waits for 5 milliseconds or so before it responds, before the sound comes on. So this is quite sluggish. Do you have any idea where this sluggishness comes from? You remember last lecture? Probably quite alien to you, that all this concept. It's the travelling wave in the basilar membrane, in the cochlea. Sound arrives in your ear. It makes the basilar membrane vibrate, and this vibration travels to the point of where this neuron sits. It takes 5 milliseconds, so we're always lagging behind a little bit. Then it will go into very high onset, that's called onset response, and then it adapts over time. When the sound is switched off, it goes back to zero almost, and then it goes back up to something which is called spontaneous activity, because every neuron is always active randomly, without any stimulus on. Why that is a good question. I could speak for hours about that. Just accept it. It's a really good way of changing the working point, so you can also code negative half waves of the sound with that way. Most interesting is really where this adaptation here comes from. We have research grants to explain where this adaptation, what that actually means. Does your perception adapt over time? Hell yeah, it adapts all the time. The visual system, it might be a bit more obvious, although not necessarily. That, for example, one kind of adaptation that we are all aware of is if you have an ongoing sound, pure tone in the background for a long, long time, what happens with your perception of that?
You don't hear it anymore.
You start to ignore it over time. You hear it at first few minutes, and then you start completely, it blends out. And when you switch that sound off, you suddenly know, oh, it was there. That is adaptation. And neurons show exactly that behavior. When something changes, they respond a lot, and then after even 10, 20 milliseconds, it's boring. That's basically what it is. Once it's there and it doesn't change, it doesn't carry any information anymore. The neural system is only interested really in changes in the environment rather than the pure signals. This is why language is developed to change a lot. When I'm talking to you, the changes are in the range of 10 to 20 milliseconds, and it keeps changing over and over again. Okay, a little bit about loudness. How does our brain know how loud a sound is? Well, we can record now this just a number of spikes from one of these neurons in response to sound 20 decibel to 80 decibel. Here's a decent range. This is what the threshold is, somewhere around here where it starts responding. And then there is a very fundamental issue that I'm going to raise very briefly, but I won't explain, is namely, you have a concept of what a dynamic range is, don't you? What is the dynamic range of this neuron? Between 20 and maybe 50 decibel, 30 decibel. Because in this 30 decibel, the response of the neuron actually changes. Above that, it roughly stays constant. Below that, it stays constant. So this neuron will not carry information about if the sound is 70 or 80 decibel loud. It can't, because it just responds. It will only tell you something between 20 and 50 decibel. And that's true for every neuron. So every neuron has a dynamic range, 20, maybe 30 decibel. But surprisingly, our range of hearing is a little bit larger. And here might be a little bit of an explanation how that comes. The range of hearing that we're talking about is 100 decibel easily, 120 decibel. So 0 decibel by definition is a hearing threshold. Not quite by definition. 120 decibel is where we stop measuring because it becomes painful. So in between, somehow neurons need to do something with that. One of the solutions how we know that neurons are doing that is that they start responding at a different threshold. So here are 3 kinds of these neurons. And there's actually an interesting correlation with their spontaneous rate, that's what I said, and the relative threshold. Namely, 0 dB threshold will all have a very high spontaneous rate. So if you think of this neuron as a very nervous entity sitting there waiting for a sound, they're just always in very close to firing. That's why they fire regularly as spontaneously without any effort. And that's why they start firing at very low thresholds. You have a second category of neurons that have much higher thresholds that don't have any spontaneous activity. So that one, for example, will only start firing at 70 decibel. So that's how our auditory system is the first approximation how our auditory system solves this problem of the dynamic range, namely splitting it up into neurons that have a low threshold, middle threshold, high threshold. If you put them all together, you get our general hearing threshold, or our hearing curve. If you put all of these together, the one curve that I want to show for a normal hearing person, it's the red line, this is the sound pressure input here, between 0 and 110, so the whole range. Now if you measure the response of the basilar membrane, it could be the just how much it vibrates. It would translate, that's not a sound pressure level, that's a decibel level of amplitude, for example. It would look something like that. So if we're deaf, in fact, this would be a linear relationship. If you put 40 decibel in, you get 40 decibel out. If you get 80, 90 decibel in, you get 90 decibel out. Okay? But that's not what our ear does. Our ear amplifies sounds. I explained that last time. This amplification leads to a shift of this whole curve to the left, so that even at 0 decibel, we still get a response of the basilar membrane. Problem with that is, if we just do that and amplify everything by, say, 40 decibel, what happens to 100 decibel? Does 100 decibel become 140 decibel? Obviously not, because that is damaging and wouldn't be very convenient. So the auditory system compresses that range And this is a really interesting curve because it carries a lot of information about the normal hearing. So you have the threshold at 0 decibel, then you have this steep going on, which is usually 1-to-1 slope, and then about a third of the slope up to higher amplitudes. So that's what the perception, what we know from the basilar membrane, how we perceive the loudness. Now, the general perception of loudness, you've probably seen something like that. Just we measure it in Pascal or in decibel. You know the definition of dB SPL? Yep, so I don't need to show you that. This is the threshold of hearing at 0, it goes up to 140. And here are the PSIs, or the Pascals here. Who knows it? What's this threshold to the definition of threshold? 0 dB, sorry, not threshold.
The reference.
Yeah, the reference pressure, what is it?
Atmospheric.
2 times 10 to 1 to
5.
Times 5.
Good, well done. And it goes up to 100,000 pascals. So there's a range of 14 orders of magnitude that we hear, which is quite amazing if you think about it. That really. So what's there must be some scaling in there, because for us it doesn't sound 100 trillion times louder. How much louder does it sound? That's the question. And here comes the unfortunately very complex answer. Loudness and intensity, as we measure our sound pressure level, are unfortunately not really correlated. The sound pressure level that we measure with an dB meter is a physical measure, because we can measure pressure, but we cannot measure perceived loudness. And here I'm explaining there's the first of these measures where we have something it's a subjective measure that we cannot 100% predict. So how do we define that? First of all, it's a subjective measure. The first definition of this subjective measure is related to 1000 Hertz tone. That's the definition. Namely, that's the measurement of the phone. And the definition of a phone is that a 40 phone at 1000 Hertz tone has also 40 decibel. So that's the first definition, how we try to objectify a measure of loudness, because we're quite often interested in how loud something is, because the perception of loudness is arguably more interesting or more important than the sound pressure level. Simple example, you can have an extremely high sound pressure level at 10 Hertz. You don't bother because you don't hear it. You probably would feel it. But you can have an extremely high sound pressure level at 100 kilohertz. Your bats in the garden would mind, but you don't mind. So we need to know what is bothering people, or how they perceive the amplitude, or not the amplitude, the loudness of a sound. Now the first definition is this phone, and this is working only with pure tones, and we start with 1000 Hertz tone, and then we can create a line. All of these sounds as pure tones sound equally loud. Okay, it's a nice way. So the definition is loudness of n equals 1. I'll talk about zone in a second. Talking about the connection between zone and phone, and 1 zone is equivalent to 40 phone, which is the loudness level of 40 decibel of a sine wave with a frequency of 1000 Hertz. Kurt Tucholsky says nicely, noise is the noise of others, and the dog makes no noise. There are many kinds of noise, but only one silence. So it is, that's just saying, it is a subjective measure. It's a personal subjective characteristic of a sound, as opposed to the sound pressure level, which is objective and measurable. We can extend that. There's an ISO for that. We can extend that 40 decibel or 40 phone level to any. This is the hearing threshold level, obviously 0 phone, up to 100 phone, and then these look a bit like that, these curves. Okay, so that gives us one way, if we want to know how loud something is, or perceptually is, we ask the person to adjust the 1000 Hertz tone to be equally loud. And then we have, and because we then know how loud this 1000 Hertz tone is, we know that this person would say, okay, this sounds like 70 phone to me. Okay? But this is still not trivial. There's a different, another measure that is equally often used, which relates to the actual perception of the loudness. Because, be careful, 80 phones in here is not twice as loud as 40 phone. So what is twice as loud? This is where the zone comes in, derived from Stephen's power law, namely that if you double the loudness, you get a 10 dB increase of intensity perceptually. And the definition of that, the easier or different way of measuring the loudness is the zone. And the definition of that is that 1 zone equals 40 phone. So a 1000 Hertz zone at 40 decibel is exactly 1 zone. And now the zone scale is a perceptional scale which doubles. So if something is twice as loud, then you get 1 more zone. And you get every 10 dB, you double the numbers of zones that you have. That works well for everything above 40 decibel, because you see it's a straight line above 40 decibel. Below 40 decibel, this curve isn't flat anymore. This is why it's not trivial, this connection. And we need to be careful with sounds above 40 decibel and below 40 decibel, because the perception is slightly different. Now, how do we model that? The easiest way of modeling it, why do we want to model it? Because if we model something, we can maybe predict how the perception of somebody would look like. And we can maybe measure it as well, objectively. Objectively means I can maybe put an EEG on my head, and I know I perceive this as 40 zone. And the model there would be, it would be proportional to the activity of the number of neurons that are active at every point in time. And that's a relatively good model, but it's quite complex to actually measure that, obviously, in the real world. Okay, here's a comparison of loudness, just as an overview, between, well, the Pascals, the SPL, and the zones. There's always an approximately there, because this isn't a physical connection between these two. This is physical, this is perceptional, and it depends on lots of things. It depends on the frequency range of things. It depends on the temporal time course of it. It depends on all sorts of stuff. But you can see roughly, well, 1 zone, normal talking 1 meter distance is about 1 zone. And if you double that, or double it again, you get 60 decibel TV set, and so on. The zone is a nice measure because it has a useful range of perceptual measures. Okay, just summarizing, the loudness in zone at the loudness level in phone, as shown, is easily converted. We have a nice correlation between these. But the psychoacoustic perceived loudness level and the objectively measured sound pressure level in dBSPL cannot be converted. There is no formula. The typical question, how to convert half a zone to a decibel, cannot be answered. Only a pure tone of 1 kilohertz measured at phones is equivalent to a dB. So unless you always have exactly 1 kilohertz tone, you cannot actually say how loud something is, unless you ask somebody. Distinguish carefully when looking at the volume, that's the magnitude of the sound. The zone is part of the loudness, phone is part of the loudness level. Try to avoid layman's terms intensity. dB or dBSPL is the sound pressure level, obviously, and dBA, you probably have heard of that, is the evaluation, is a measurement for a simplified evaluation. A dBA, I'm sure you all have seen the filter of a dBA. The dBA works, this is the actual definition, it goes between 0 and minus 40, is the dBA has been invented in order to predict the loudness for roughly reflecting our frequency perception curve. So for low frequencies our perception goes down, but our thresholds go up, and for high frequency they go up as well. Obviously this is not a very good approximation, it actually goes down much steeper in the real world. But the point that I want to make here is that you need to be careful, because this has only ever been intended for 40 decibels sounds. Most amplitudes that we measure in the real world are much, much louder than 40 decibel. And so you always buy yourself a lot of error, first from the fact that it's louder than 40 decibel, and secondly from the fact that it is not actually fitted to the frequency spectrum that we perceive. So loudness, very difficult. Sound pressure level is easy, but what we perceive from that, there have been whole books written about how we actually perceive it. But now you have tools on the hand at least to understand what a phone and a zone is, and how we can subjectively measure it. One important question always is, once we say, okay, this is how we perceive it, is the next question is, how do we discriminate them? And the discrimination of intensity is about 1 decibel for normal listeners. Depends on the frequency, depends on the loudness as well, but this is the one number I want you to remember. That's why the decibel is actually a really useful measure. The other question, why do we not measure something in bell rather than decibel? That's probably the answer, because 1 decibel is actually about the J and D, the just noticeable difference between a sound. You can differentiate 5 decibel from 6 decibel. You can differentiate 80 decibel from 81 decibel. It's roughly constant. And that's about the Stevens law, by the way. We talked about that much, but this is a really nice, unique number. Okay. Let's go back to our hearing range, and let's come to pitch, frequency. What's frequency? What's pitch? These are different things. This is the speech banana. Have you seen that? That's the frequency that we perceive, 125, 5K. It goes higher obviously, but here it's mostly about speech and music. This is the range as audiologists plotted, namely upside down for some reasons. Here it's the other way around. Here's from sound pressure levels going up. Here it's upside down. So this speech banana in here would be that way around in there. Well, hang on. This is the actual sound level. This is the loudness level. So this is 0 dB hearing level is our threshold. So this curve is equivalent to that wiggly curve down there, because that's threshold in hearing. This is relative to threshold. Okay. So this gives you called speech banana because it gives you a nice, picture-like overview of what is where. Low frequencies, dog barking has also high frequencies. Medium frequencies, high frequencies, and low amplitudes, high amplitudes. Interesting for our purposes is, two things here. That the speech banana in itself, it has all of these letters in there, and these are actually roughly the center of gravity of the where these letters sit. So the U is, for example, is not very loud, 40 decibel. In the speech range of about maximum around 750 hertz. R sits around there. E back there. Lower frequencies. That's because the formant frequencies are lower at least. And these are all the vowels, roughly, because we have a lower pitch. This is where the frequency, the amplitude for the vowels sit. And all of these are the consonants. The especially very, very high frequency, have most of their frequency above 4K, which is a problem if you have a hearing loss. Never really talked about hearing loss, but you might know hearing loss affects the high frequencies first, and the typical hearing loss would cut off something like that. You hear all the vowels, and then it cuts right through there. Nice, interesting experiment. Older people have very often problem understanding the difference between singular and plural, because the only difference is this at the end of the word, and that's not audible for many people. Yeah, we extend that. Here's the equivalent speech range. Music range goes higher and louder, and the whole audiometrical audibility limit there is even bigger for that. Okay, this is where we communicate and all of that. Right. Okay. Pitch. You know the definition of pitch? You should know the definition without looking. What's the definition of pitch? No? You musicians? How would you define pitch?
Perceived frequency.
Frequency is something in it?
Yeah, it's frequency, but perceived one.
Yeah, it's like loudness and a decibel. Certainly it's this subjective measure of something that is physically there. But what's the basis of what's physically there? Good question, because that question hasn't got an answer. But what do you define pitch? What's the signal that has a pitch? What can you do with it? Well, close to your heart. The official definition of pitch is that one here. Pitch is that attribute of sound of which I can make music with it. If I can order it on a scale from low to high, then it's pitch. This is a really silly definition, but that's the one that we have. Because if you try to define it in any other way, there will be somebody standing up and say, no, that's not right. But the take-home definition is, if you can make music with it, then it has pitch. But pitch is not frequency. But both are measured in hertz, and there is a very substantial difference between the two. And this bit what we equivalent frequency, certainly of pure tones, is what we measure, and pitch is what we hear. And there are some very good examples where these two are definitely not correlated with each other. Okay, here's my first example. We often perceive a periodic sound as having a pitch. The periodicity is a very good marker of pitch. If something repeats, you will attribute it to a pitch. Talking about that in a second a little bit more. But let's just make an example. This is a pulse train. Let's see if we hear that. Pulse train means this is just acoustic pulses just going up and down. And this is 10 times per second. Is that music? Certainly not. Let's do doubling it. 40. Now that one here, does it have a pitch? I hope you say yes now. What's the relationship between these two?
What?
The relationship, the harmonic relationship between these two.
Octave.
It's an octave, yes. So an octave means you can order them from low to high, and you can make music with it, so there's a pitch in that. But the interesting thing in here, the really interesting thing is, nobody is in doubt that this thing has a pitch. Oh, that one. But what about that one? Does that have a pitch? Yeah, that one. No. Something happens between here and here, depending, it's subjective a little bit, but between 20 and 40, something happens where the perception changes. That's really interesting, and let me just go a little bit about evolution here, because what's happening and what pitch is a really clever trick of evolution to save effort. It's nothing else. Because with 10 hertz, you hear every individual click and you can follow it. Put that into connection with pictures, with moving, with a film. If I give you 10 pictures per second, you can, you see it flicker. You see almost every picture individually. If I give you 20, well, certainly if I give you 40, this is film. You don't see individual pictures anymore, you see the movement. And something very equivalent happens here. Namely, here with 10 hertz, the auditory system cares for every individual pulse and gives you a representation of that in your head. 20 as well. With 40, it doesn't bother with that anymore. Maybe because it can't, but probably because it can't. But what it does instead is inventing something new. So like in the video, you get a film. Now you get an additional quality, which is pitch. which is just a shortcut of saying, yeah, we've got a pitch. I like higher pitches more. Plus a timbre. And these two qualities define your whole perception. Timbre and pitch, well, and amplitude as well, but well, loudness. But that's my point. The evolutionary background is that hearing has started in fish. I talked about that last time. You remember the lateral line organ of fish. I was talking about the only method that fish have underwater to produce a sound. You all have a good understanding of physics. Think about that for a second. How can a fish produce a sound? What do you need to produce a sound? You're the perfect people to ask because you're building musical instruments, don't you, in this course? You need an impedance change, an impedance boundary. That is the most frequent way to produce sound. Namely, you put two things with different impedance together and knock them, and then the result is sound that is going into every direction. Now, if you're a fish, imagine what a fish consists of. All of the material that the fish has exactly the same density, which is virtually almost the same density as water. So it doesn't have anything to produce sound, apart from its swim bladder, because that's filled with water, with air, and the air and the water produce a boundary of impedance, and that can be used. So what a fish does to produce a sound is to open and close the swim bladder. Makes a sound like a click, or an impulse, not unlike this. And people never believe me, but if you put a microphone underwater in a fish tank, they'll communicate all the time. You just don't hear it because it's quiet, and our ears are not tuned to that. But what they do, it doesn't sound very different from that, because that's the only thing that they can do. They can just make it boop. They haven't got any fancy equivalents to our vocal folds or something. So, what is the question is, why do they do that? They can communicate with that. They can tell each other where they are, and because of the size of the swim bladder affect the resonances, they tell each other how big they are. That's basically the only information that they can communicate, and the only information that they need to communicate. But now at some point in evolution the trick has happened, namely they went beyond the limits of where neurons can resolve that, namely up to here. And instead of following every individual click, which doesn't make sense anymore because they're all the same anyway, coming from the same fish, from the same direction, some fish in 150 million years ago invented pitch. And pitch is like a color. It just says, yep, it's that pitch, and it's a glorious shorthand for covering or for capturing a lot of information about that sound. And we still do it today. In fact, I'm telling you all of that because this is how evolution works. Once you invent something, it usually never gets discarded again. So all of our brain structure, the basal membrane structure, the cochlear nucleus structure, all the structures in the brain where sound is processed, are still extremely similar to what the fish 180 million years did with the fish. We've put things on top, up to the cortex, that interprets that the fish doesn't have. But all the brain, the brain stem functionality is surprisingly similar. Okay, let's explore two different stimuli to find out what how we perceive pitch a little bit more. Namely, two extremes is the pure tone and the individual pulse or a pulse train. That's the ones that we already heard. So tick, 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 tick. And this is the pure tone as the equivalent, has the same periodicity, but different frequency spectrum. Spectrum of that is just one sound here. I think it's always 100 Hertz it's supposed to be. If we have a square wave, we've got all the odd harmonics. If we have the pulse train, we have all of the harmonics. If we just have a single pulse that hasn't got any spectral information, white noise and short tone, they're just for completeness. We concentrate on these two because they illuminate two different concepts of hearing. which I will come, or namely the temporal and the frequency perception of pitch. And we have two. I'd say that first we have two ways in our brain how we perceive pitch. One is measuring time and one is measuring frequency. And we know that as we explain that. The aspect of a sound that leads to musical perception is pitch, everything else is timbre. Sound with the same pitch can have different timbre, obviously, otherwise you couldn't play music in an instrument. And you can have the same timbre, but different pitch. That's just meaning you play a different note on the same instrument. There are two kinds of models how we to understand how our brain is actually analyzing that. One is temporal, measuring time, and the other one is place, measuring frequency. Why it is place we come to in a second. They're associated in both ways to the way that neurons actually code frequency in the brain. And this takes a bit to explain. Usually we don't have simple tones like pure tones. They're very rare in nature. These click trains are actually a little bit more often realistic sounds, with the exception of that they have a flat spectrum. If you have a click train, a pulse train, this is the spectrum of the pulse train, and you modulate the envelope of that, it can sound like anything, like an R or an E. All the periodic sounds are a good model. So the pulse train is a very good model of a natural sound, but it doesn't have any envelope structure here. So what happens if we send that to our auditory filter bank? Now remember last week or 2 weeks ago? Yeah, that's a long time ago. But our basilar membrane consists of auditory filters that we were talking about. And on a linear axis like that, our auditory filters would become broader and broader. That is because on the log axis they have roughly the same width. Yeah, remember our ear perceives sound logarithmically. That's why the octave is so important, because the octave means you go in the same distance across the basilar membrane. But here we choose to plot it in a linear fashion. It's a different way of plotting it. So we have very narrow filters here for the low frequencies, very wide filters for the high frequencies. Now if we have a filter bank like that, so not same width but different width, and we analyze or we send our pulse train through that filter band, then we get a response pattern that looks like that. Get an excitation pattern as a function of frequency, and because we've got very narrow filters here, there's only one or few components of the pulse train in there, so we get something which is called resolved harmonics in there. Whereas in the high frequency, the other extreme, this filter that sees all of the frequencies here, and they all overlap, and so the excitation in that filter is just flat. Yeah, does that make sense? Have you heard about resolved and unresolved harmonics from music? You know what a harmonic is, don't you? Okay, we'll talk about resolved harmonics, I think, a little bit. But this is a pure psychophysical / musical terms, resolved and unresolved harmonics. If resolved harmonics means you can actually hear these out. So if you have a very good auditory system, a very good ear, is there any absolute pitch perceptors among you? No. If you have an absolute pitch, and there are few of these around, as you might know, they actually hear these individual bumps. With our normal ear we wouldn't hear it, but the information is there for us. And resolved harmonic, it means we can do things with that. We can, for example, we can mistune them and we would hear the difference. If we mistune something up there, we wouldn't hear it because it's unresolved. So this is a concept which is very important for us. It also determines pitch, is determined by these resolved harmonics. So the low frequency parts of an instrument will determine the pitch much more than the high frequencies. Because of the concept of these resolved harmonics, because they will be represented on the basilar membrane very well. Okay, what is represented on the basilar membrane? If we look at the basilar membrane vibration, here is a function of time that goes downwards. Let's say the first one, 100 Hertz. Basilar membrane just goes up and down very easily. If we go higher, it's like a little bit like a low-pass filter. It will not follow it completely. If we go even higher, we get a modulation. Why is that? Where does this modulation come from suddenly? It's a $10,000 question.
We have two very close together.
Yeah.
Within the same filter.
It's not only two,
Or a non.
you've got a lot of them together. And what do they produce? They produce a beating, nothing else. Because, just translate that, this is a 100 Hertz pulse train. So how often is there a pulse in time? If you plot that in as a function of time, what's the periodicity? 100 Hertz?
Between 100 per second.
Yeah, 100 per second. How many milliseconds is that? 10 milliseconds, exactly. So 100 Hertz filter, 100 Hertz flick train would have a pitch of 100 Hertz and produces a repeatability, or has a repetition rate of 10 milliseconds. So look here, these are 10, 20, 30 milliseconds. This is the modulation that we see here. And the higher we go, if we go to very high frequencies, we actually see our pulses again, because this is this is how the stimulus waveform looks like in the time domain. In the very high frequencies, it almost looks like the stimulus, because the basilar membrane cannot vibrate that fast, obviously, and it will start following the envelope rather than the fine structure. So here, the 100 Hertz channel, although it has, well, the 100 Hertz channel is somehow special because it's maximally tuned to the envelope. So you've got a very high amplitude in there, but it's just a pure tone. So it's like a Fourier transformation. If you Fourier transform that, then the 100 Hertz component would be very strong, obviously, because we know it is very strong from here. But if we go higher, we just get less and less, but at some point we get actually the modulation. So in the low frequencies we get fine structure, and at high frequency we get the envelope information of these two. And this is related to the envelope we get the unresolved, and in the resolved range we get the fine structure. Okay. What happens, just out of interest, if we take all of these away? I think I haven't got that demo, but I should play that. Imagine I take everything between 500 away. Would the sound still have a period? Well, would it still has a 100 Hertz pitch? Pitch is determined by the periodicity. What is the periodicity of the sound? Like that. Periodicity is still the difference between these frequencies. The beating frequency is still 100 Hertz. That's the phenomenon of the missing fundamental. I really should do a demo for that, but you have to believe me that it sounds, the timbre is different, but the pitch of that sound would be extremely the same. Very simple everyday example is the telephone. What's the lower cutoff frequency of the telephone? It's about 340 Hertz. So we cut off these. And what's the higher frequency range? Well, it's about here. It only is a bandpass filter, the telephone. That's everything through between 340 and 3.4 kilohertz. Everything else is cut out. And we still have no problems hearing pitch over the telephone. Sounds a bit tinny, but that's mostly the effect of the missing high frequencies. But the pitch is completely left alone. And what's behind that? Because the pitch doesn't have anything to do with frequency. It is only computed, in that case, via the envelope, which is a time domain, not a frequency domain effect. Okay, here are the two theories, how we perceive the pitch. Here's, for example, the two sounds, 500 Hertz and 550 Hertz. You hear the difference? How do you hear the difference? There's two ways that the brain could do that, and let's see which one is true. One is what's called the place code, namely if I look at the basilar membrane motion of these two, They both have slightly different activity patterns on the basilar membrane. In other words, slightly different neurons in the auditory system are active. And you can make a little filter or something on top of that which looks at the maximum, and this maximum is slightly different from that maximum. That gives you a way to determine that. The other way is temporal coding, or temporal mechanism, which is effectively just to measure the periodicity of the sounds. And what neurons do is, well, you have to believe me there, I can't give you evidence, is that these are supposed to be spike trains, and in a 500 Hertz tone, the neuron would fire with either the periodicity of that sound, which is 2 milliseconds, or with the multiple of the periodicity, because it cannot fire enough. So it's either 2 milliseconds, or 4 or 6 milliseconds, but always a multiple of 2 milliseconds. And the inverse of 2 milliseconds is 500 Hertz. And in this case, 550 Hertz, they just go a bit shorter, so then it's multiples of 1.8 milliseconds. So the information is there in either case. Here is the information, slightly different groups of neurons respond. Here the information is the same neuron response, but slightly different intervals. Okay, so which of these is true? First of all, what you would need if you have the place code. They have this template matching system that has been suggested in the 70s. Let's say we have 100 Hertz tone. This is a 100 Hertz, 200, 300, 400 Hertz, and we have we want to what is it, 500, 550 Hertz, and we have templates in our brain because we learned them somehow, and we can use our template. That's the hypothesis here at the moment. We can use these templates to put them on top of the spectrum of both of these, and the template that fits better will tell us which is our sound. So here we have I should use the 500, 550 analogy, but we have here is a 300. Is actually, if we have a component at 300 and to 200 and 400, we have an amplitude modulated sound with a fine structure of 300 Hertz. My point here is that either a 100 Hertz, does it fit either the 100 Hertz template, or does it fit the 110 Hertz template? And you would say, yep, it fits the 100 Hertz template better, so this one would light up, and the 110 Hertz template doesn't light up. That's the sort of the way that the visual system quite often works, and it's easy enough to understand. And that has been in the 70s the standard way of explaining how we perceive pitch, namely by learning it and learning templates to put on top of the stimulus, the music, the speech. And you have different templates. You need to learn a different template for every musical interval or for every musical sound. The alternative theory, obviously, well, template measuring must be learned somehow. It works best at low frequency, where we have the resolved harmonics. It doesn't work at higher harmonics because we don't have resolved harmonics that we can put a template on top. So the alternative theory is the temporal model. So we've got our 100 Hertz complex sound. This is our pitch train, clack, 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 but much, much faster. And we have, as we saw on the basilar membrane, either the fine structure or the envelope coded in there. But what neurons do out of that is quite interesting, because neurons will fire mostly when there is a large amplitude, and not so much if there isn't very much amplitude. So if we had 5 neurons and these 5 channels, this one would be, it's called phase locking. They would phase lock to 10, 20, 30 milliseconds. And this one would phase lock also, but here to the envelope and here to the fine structure. And the ones in the middle do something a little bit of both. They fire sometimes because of the fine structure, sometimes a little bit of the envelope, and this one doesn't actually code anything really. But the trick is, if you sum them all up and calculate the interval statistics, you'll find that there's always one at 10 milliseconds. So you do a bit of statistics with these, and you just sum all of this up, do a histogram, and the histogram maximum will be the pitch. Now that's a viable hypothesis, how we hear the pitch. Effective way of extracting periodicity, you may just measure the time interval between the periods, or in fact between the response of the neurons. Can explain the pitch perception most similarly. And the neural mechanism for that would be an autocorrelation measure for all of these, summary autocorrelation for all of these neurons. But funnily, although it explains most of the perception of pitch, there's no evidence for that, not for the lack of trying. So since the 70s, there have been hundreds, thousands of researchers trying to prove that this temporal pitch is in fact the way that we perceive pitch. And there is nobody out there that I know that doesn't believe that the temporal pitch is a good mechanism to listen to pitch. But there's no good evidence from brain, certainly not for the autocorrelation. There's still a lot of work to be done. So the exact mechanism is not clear today, but it is, as a take-home message, it is most likely a mixture of these two. So for low frequencies, the resolved harmonics, there is very likely a pattern recognition system going on that you have to learn. That's why you learn the resolved harmonics. And for the higher frequency pitches, it's a temporal mechanism where you measure the intervals in between, the time interval between the periodicities. And the crossover point of these two is around 1000 Hertz. So below that, I would call it a low pitch. Above that, it's a high pitch. Perceptionally, you don't hear anything happening with this. Perceptionally, what's actually the range of perception of pitch? The low range we discovered here is about 20 Hertz. What's the lowest tone on the piano? It's about, I think, 33 Hertz, if I'm not wrong. And that's not very musical, but it's still roughly right. What's the highest note on a piano? 4,500, I think. That's where pitch perception ends. Above that, you still hear if a sound is higher than the other, but the JND for it goes up massively. So there's no point in trying to do music with that anymore, because everybody hears the difference of a semitone at 1000 Hertz, but nobody hears the difference of a semitone at 10,000 Hertz. So there's no point in trying to make music. It sounds awful. Well, that's probably related to that. It sounds awful because we don't need to listen to pitches of that height. And why not? Because it's not relevant, because they're too fast. That's the actual reason. 10,000 Hertz pitch would be, 1/10,000th of a second, 0.1 milliseconds, and our neurons are just not fast enough to do that. They can cope with anything up to 4,000, 5,000 Hertz. If you're a barn owl, it goes up to 10,000 Hertz, but we humans can analyze times up to 4,000, 5,000 Hertz. So 0.2 milliseconds is about the width of an action potential. This is what we can work with for terms of pitch. Above that, our neurons fail, and we do not interpret it as a temporal pitch anymore. We still have a place mechanism. That's why we hear that a 6,000 Hertz tone is higher than a 5,000 Hertz tone, but we do that by place and not by time.
So what is it in hearing systems of different animals which allows them to have that perception at higher frequencies? Is it something physically limiting us, or is it just the way that our...
Well, it's a good question. It's always a good question. Why have we evolved to do that? What is the hen and the egg? Maybe we don't need it. That's the basis for it. We don't need it. Full stop. That's why evolution hasn't developed it. That's the answer that I would give. Barn owls need it because their prey is mice, and mice communicate at higher frequencies. So the barn owl needs to hear that, and that's why they are more sensitive for higher frequencies. That's why they have evolved mechanisms to listen to that. Every mechanism like that takes energy, and if you're willing to spend that energy, then you could do that. There are animals that have even higher. I mean, the favorite example are bats. They hear up to 200 kilohertz, and they have a very high resolution for temporal codes as well, because they echolocate. They need that, but they spend a lot of energy in doing that as well. Energy or brain area. They spend, I mean, 2/3 of their brain is covered with the auditory system. For us, 2/3 of our brain is taken over by the visual system. That's just a reflection of how important one or the other is. So I guess if you put people into situations where it is evolutionary, where they, in order to survive, have to discriminate 8,000 hertz on a temporal basis, after a few 100,000 years they probably would be able to do it. What they do is they change the molecular structure of the neurons in a way that they are temporally more precise, but that costs energy, and we're not willing to spend that energy. Okay, the last perceptional example is space perception, which is interesting because that's the one system that we understand best, I think, in terms of neurons and how we analyze the space around us and how our brain is actually doing that. Here's the definition. I have in the middle the medial plane, we have the horizontal plane, and we're obviously quite good in discriminating that. And the cues that we need for that is twofold. Namely, if the sound source comes from a direction somewhere than the side, somewhere else than the front, then the sound will be louder on one ear, and it will be phase shifted. The phase shift comes from the different arrival times. So this ear is slightly earlier than the other ear. These are called ITDs and ILDs. ILD, interaural level difference. ITD, interaural time difference. And these two are almost fully sufficient to explain sound perception and localization, but not sufficient for the elevation, because all of the sounds on what's called a cone of confusion have the same ITD and ILDs, so you need a different mechanism to differentiate the elevation. Do you remember what mechanism that was? Talked about it last time. That's your pinner, the shape of your pinner, because that's highly asymmetric, and it will create a different filter shape or a head-related transfer function depending if the sound comes from there or from there. Okay, yeah, that's what I say, vertical plane. These are just two transfer functions from a sound that comes from above and from the front, and you see that they have this characteristic notches depending on where a sound comes from, and this is the theory at least, is that these notches is what we're very sensitive for. So depending on where the notches in the spectrum is, we can associate it where in the azimuth our sound comes from. How good are we? That's measured by the minimum audible angle, the MAA, and is about, if we just plot, if we move a loudspeaker very far away from us in the horizontal plane, we get ideally at around 1000 hertz. That seems to be the ideal frequency, about 1 to 2 degrees. That's quite surprising. I mean, 1 degree is almost nothing. It's really, really good resolution. Not as good as the Barnolds again, but as actually, because our heads are relatively big, we have an advantage, because we can make the better effect of longer delays between the two ears. If we go slightly away from the front line, we get worse. It's as simple as that. And we're really bad over there, although we have the highest ILDs and the highest ITDs. The difference are not very big, whereas in the front the differences are the biggest, so that's why it's useful. That's the answer as well. Why do we have two ears? Okay, so the point here is the cues for localization are individually different. But with loudspeakers, why do we not have finally loudspeakers in our television that gives us a nice 3D virtual sound experience? The reason for that is crosstalk. And the only way to get a realistic representation of sound is via headphones. But the headphones need to know your head-related transfer functions in order to produce a sound. If they don't do that, you get a phenomenon which is called lateralization. You hear the sound usually inside your head. everybody knows that. It's not very nice. Well, you get used to that. So, well, it's not nice. We're used to it for 20 years, so that's why we don't bother with that. But actually, it's quite weird, isn't it? You put a headphone on, and you always have the sound coming from the middle of your head. But there's nobody in the middle of your head that makes the music. Why is that not actually a crazy thing? And why haven't we developed things that make the sound coming perceptually from outside of the head? Well, the answer is we have, because the cue between that, or the difference between that, is the head-related transfer functions. We actually can do that. This is a chema, and the way to do that is to measure for the chema here in this case, all of the transfer functions from every different angle. And if we have these head-related transfer functions, we can convolve the signal with them, and we could, for the chema ear at least, it wouldn't be a difference then if the sound comes from the headphone, convolved with the head-related transfer function, or from an actual sound field. Now, why isn't that implemented in every headphone in the world? I don't actually know. One of the issues is that the ears are slightly different between people. So we can do it for the chema, but not your ears are slightly different from chema's ear, and that's why it's not perfect. So people have resolved to not head-related transfer function anything, so the sound is always coming from either in the middle of your head or slightly to the left or to the right, but it always sounds inside your head and not outside. There's a lot of work to be done. I think there is a market for proper headphones. Well, it's not the headphones, it's the transfer function. There needs to be a little preamp that knows about your specific individual sound. Imagine you go to Tesco, somebody sticks a probe into your ear and it measures your individual head-related transfer function, and you would then be able to listen to any recording as if it's real. There's actually somebody 10 meters in front of you over there making the music, and not a little person inside your head. So, if you want to make money, there's certainly some openings in there. Okay, and here's my last slide. Going back to the beginning, I am a physiologist, and this is a really old model. It is maybe not exactly exact anymore, but it's a really good way of understanding how neurons can actually do something to tell us about the outside world. So the logic here is, these are the two cochlea. There's a sound wave coming from the front. They start neurons firing, and you see, that's in slow motion, how the action potential travel as a little dot. And what I've never mentioned is that these don't travel with the speed of light. They actually travel relatively slow, namely about 1 meter per second, which for our body size is not that fast. And they take a few milliseconds, or a few hundreds of a millisecond at least, before they go from the ear to the brainstem. This is very rough. This is just the brainstem on the right side. We have a mirror of that on the left side as well, but we only plot the right side. And now observe what happens with these neurons. They're called delay lines, because this neuron here has a shorter delay than this neuron. And here they come, here they travel. So this one is ahead, that's fine. And it keeps traveling, and it goes to that neuron, that neuron, that neuron, that neuron, that neuron, and bang! Neuron number 2 gets both of them at the same time. Now the sound comes from the side, so this one fires first, this one fires second. So this one has a little bit of an advantage now against that one, the racing cars, and it can travel a little bit further down. So it's not number 2 that is active now, but number 6. What I forgot to say is they only can become active if they get more than one input at the same time. Yeah, it's called coincidence detection. But what that together does is, it explains, it's a little neural model, it's a simple model, but it translates temporal difference into a map of the world. Because this is a map. 2 means sound from the front, 6 means sound from the side. And this is how our brain works, with maps. Everything works with maps. Frequency map, for example, as well. I've got a 4,000 hertz map there. These neurons respond to 4,000 hertz, neurons respond to 5,000 hertz. And here we've got a map, neurons respond from the front, neurons respond from the side, and so on, so on. So this has been around for 60 years now and has inspired lots and lots of research. And they're good models have explained pitch perception in a similar way, namely with these delay lines, to measure the difference between the arrival times, not of left and right ear, but between the periodicities of first period and second period. You have a delay line, you can measure the interval between these, and that gives you a map of pitch. And yeah, you still find research papers every year that measure these pitch maps. They're not easy to find, but that's the way that we hope to resolve the issue sooner or later of how our brain perceives it. Yeah, that's how they do it. So what we loudness, pitch, localization. These are the three main perceptions of sound. Do you know any others? Rhythm is one, but I don't know about rhythm, it's too slow. But it is one. Good.
Harmony as well. It's slightly different from pitch. No?
How's it different?
It's a combination of pitches.
It's a combination of two pitches, exactly. So what's the connection? It's really good. I've spent a good time of my life to actually understand that. Can't say that I do, but it's exactly that. In order to perceive a harmony, you need to listen to two pitches. And you need one more element, namely a memory between these two. If you have these three elements, the pitch perception of both tones and the memory, then you can create the harmony. But the harmony is, for us, for musicians, the most important aspect. It's more important than the pitches of the sounds, as long as you haven't got an absolute pitch. If you have absolute pitch, it turns out that the absolute pitches are actually more important. The absolute pitch processors sometimes have problems with harmonicity, with harmonics, because they measure the edge frequencies and then they have to calculate the harmony. Whereas for us it's exactly the opposite way around. We don't know what the absolute pitches are, but we know very exact what the harmonic is.
The difference between them.
The difference between the sounds. Well, not the difference, the ratio between them. Be careful because it's logarithmic. But anyway, the evolutionary ground for that I can see is actually quite straightforward, because in language we have evolved not to play music. Sorry, we have evolved to talk, and in speech it is completely irrelevant what the absolute pitch of somebody is. It's only important that we hear the differences, that they hear the melody of the voice, and that is the differences that it goes. Remember what I said at the very beginning, nature doesn't care about something constant, it only cares about differences. And in speech it is just an array of harmonics over time. And in music of course as well. But my guess is that music is a kind of a mirror of speech, in a way, without information, or with different kind of information, but it mimics speech in many respects, in rhythm and harmonics and so on. Well, obviously music comes from singing, probably evolutionary, isn't it?
Hitting things, I guess.
Hmm?
And hitting things.
And hitting things, yeah, maybe.
I'm sure we once used to just like hitting things, and then we started just hitting things repeatedly with a
200 times per second. Good luck with that. No, but you're right. I mean, hitting, especially metal things or something, things that actually have a nice resonance is also not music. That's right. But since that is more difficult than using the natural apparatus that you carry around with you all the time, I would wager a bet that music comes from singing. Okay. Any more questions? You know a little bit better how musical instruments work now? Probably not, but how we perceive musical instruments maybe a little bit. Cool.
So, is Martin not going to come?
I don't know. I asked